So, last time around, we talked about uh, locus involving perpendicular bisectors on Argand diagrams. Now, one of the examples we discussed last time around was related to this. And we said if this was our imaginary axis, this was our real axis, and this was our Argand diagram, the way to think about this is that Z has to be a point where it is equidistant from this complex number 1 and this complex number 2. So the first thing we did is we pointed out where 1 was, our first known complex number, and then we pointed out where the second known complex number was. So they were over here. And since Z was equidistant, we essentially drew a perpendicular bisector, this blue vertical line that is right through the middle of 1 and 2. So you'd have to draw perpendicular bisectors using your compass. And hopefully you have gotten the concept and how this equation in terms of modulus kind of makes sense. So hopefully you have that intuition by now. In this video, we will extend our idea of perpendicular bisectors on Argand diagrams. But this time we won't be talking so much about equations, but we will be talking about inequalities. So let's say for our purposes, this situation was changed, and instead of this being an equal to sign, what would happen if I had put a less than or equal to over here? Well, first of all, what you want to do is you want to understand what this statement now means. So the translation of this particular mathematical equation into something that something in words that you might want to that you can understand. So if I were to translate this into words, into words that I understand, I would essentially be thinking in terms of the distance of Z from 1, I mean this, is less than or equal to its distance from the other complex number 2. So hopefully that makes sense to you. And this is what the inequality should mean, that Z is a complex number on the entire of this Argand diagram. Z is a point which has to be, which has a distance uh, such that its distance from 1 is less than its distance from 2. Or in other words, and if you think about it, in other words, Z is closer to our complex number 1 than it is to 2. So take a moment and think about this, and hopefully it will make sense. And now, given this information, if I asked you to locate a possible position for Z, what would you select? Well, you might say, well, since the equal to is still there, I mean, just like the previous example, since the equal to is there, Z could still be on this vertical line. Z could be a point here. Z could be a point here. Z could be a point anywhere on the vertical line, as thus satisfying the equal to part of my inequality. And that would be absolutely true. Z could be anywhere on this line. But what about the less than sign over here? Well, the less than sign says Z is closer to 1 than it is to 2. If you think about it, it should occur to you that that implies that Z has to be on this side of our vertical line. Z could be somewhere here. Z could be somewhere here. Could be somewhere here, or here, or here. In any case, as long as Z is somewhere on the left of our vertical line, our perpendicular bisector over here, z is automatically closer to 1. Z is automatically closer to 1 than it is to 2. Right? You can see the longer line here implying that my possible point z is closer to 1 than it is to 2. The same with this guy. Z, if this were to be Z, Z is definitely closer to 1 than it is to 2. This line is definitely longer. So hopefully that makes sense to you, and hopefully you're getting the idea that that would entail that Z has to lie on the left side of my perpendicular bisector. And thus, we would shade, and it's up to you how much you want to shade. I mean, as long as the examiner understands that you understand that the shading is involved. So just if you shade the left side of the perpendicular bisector, you are confirming that these are all possible positions of Z. This right here is the possible is the area where Z may lie, and it does satisfy this inequality. All of it makes sense. So if this was an exam question, all you had to do was basically draw this. In other words, draw your axis, point out the two known complex numbers, draw the perpendicular bisector, and make sure it's a solid line, and then shade the area that you think is consistent with the inequality. In this case, Z had to be closer to 1. So I am shading the area towards 1, then towards 2. Now, a common question again is, what if we didn't have an equal to sign? What if it was just less than? Well, in that case, our everything would be the same except our solid perpendicular bisector would no longer be solid. It would essentially be a dotted perpendicular bisector, implying that the points on the perpendicular bisector themselves are not included. That was the point of drawing a perpendicular bisector in the first place. Well, just to create this boundary, the perpendicular bisector is this boundary which separates which essentially points out where 1 and 2 are equidistant from one another. So we always want to draw this boundary, whether this question has an equal to, greater than equals to, or less than equals to. But make sure when the equals to is missing, you just change the perpendicular bisector into a dotted perpendicular bisector. All right. Now let's look into another example. This time, uh, sort of like the second example of the previous video. So what if Z was So what if the question looks something like this? Modulus of z minus 2 plus 5i. So looking at this, you can see modulus on two sides of the inequality. You can see the same missing complex number on both the sides, and you definitely figure out that this is not a circle. This has to be some form of perpendicular bisector. So we point out our axis. Sorry, we draw our axis, the imaginary axis, the real axis, and I'm going to do this very quickly, so you might want to, but make sure in your exam you take your time with this. So this is 1 plus 2i, and let's imagine this is 2 plus 5i. And we said, regardless of the question, if the question looks like that a case of a perpendicular bisector, make sure you draw a perpendicular bisector. And so in this case, the perpendicular bisector is going to be of that connecting these two complex numbers over here. So let's say this was our perpendicular bisector. Now, what this perpendicular bisector is saying is that, oops, is that any point on this line is equidistant from both the complex numbers. So this right here is 1 plus 2i. This right here is 2 plus 5i. Now the question asks, draw the possible positions of z. Well, show me where z can possibly be. Well, this one translates to the distance of z from 1 plus 2i, meaning this point, is bigger than the distance of z from this point. And if you think about it, essentially this should mean z is closer to this guy. And that should mean z is on this side, on the 2 plus 5i side of your Argand diagram. And yes, I'm sure you've noticed this, that I did not, I forgot to draw the dotted line over here. And in fact, that is true, since the equation does not have an equal to my perpendicular bisector. And I'm going to try to draw the best one I can. This is the perpendicular bisector, should be in dotted lines, right? And this is the area that you'll be shading, the 2 plus 5i, the area, the region that is above the uh, perpendicular bisector. So hopefully this makes sense, and hopefully by now you are getting the intuition of when to draw perpendicular bisectors involving Argand diagrams, what these mathematical equations and inequalities actually mean, and how to think of these in literal terms, in terms of distance, in terms of which point is closer to which and which point is further to which. And hopefully all of that comes together for you in the form of these shading and Argand diagrams. So that's all for this video. In the next video, we talk about line segments and also a few examples of where the concept of circles and perpendicular bisectors come together in a single situation.